We've been doing a few tech talks over the past few months, and we've been talking a lot about training models. And this time, Dilawar, who's a founding engineer at ZeroEntropy, is going to be talking about how do we inference and run these models, and how do we optimize the latency and the throughput for these models. So it's going to be more low level stuff. So I hope you guys enjoy. All right, I'll let Dilwar take the stage.
Great. So today I'll talk about the GPU performance engineering and why your code is ever slow, and how to think about the bottlenecks when it is being slow. So the goal here for me today is to essentially give you a mental picture on how a GPU works. And there's a lot of like optimization techniques out there which people talk about, like flash attention and Triton and CUDA, etc. But I believe that before even jumping into those topics, it's very important to understand the fundamentals, because then you'll understand those concepts much better. So let's just jump into it. So here we have two Python programs. One is it's just a very, very simple program. One is a for loop where we are doing 10,000 additions. And one is a vectorized operation, which is just adding, just doing one single vectorized call by adding 10,000. So it's the same amount of work which is happening. Um, and here I have the code for the loop, and then the vectorized that. And then if we run these, we see that the vectorized one is essentially 9,000 times faster than the loop. So we have the same GPU here, which is an H100. We have the same math. So why is the one like several magnitudes, order of magnitude slower than the other? So that's very weird, in my opinion. And you probably have heard people say that, okay, maybe because this operation is vectorized, that's because it's faster, but that's not really an answer. The answer is that these two programs are dealing with two different kinds of bottlenecks. And throughout this talk, I'll be talking about three bottlenecks. And hopefully by the end of this talk, you can look at any Python program or any program running on a GPU and tell which bottleneck it's hitting, which will then give you a better picture of what to optimize. So here are the three things. So it's very, very simple. There's no more than these three walls of GPU performance that you need to care about. So yeah, very, very easy to memorize. The first one is memory, which is that the GPU, it can't move bytes fast enough. The second one is compute, which is that the hardware itself, like the GPU, it can't do the computations fast enough. And then the third one is overhead, which is that the CPU is not able to launch the kernels, so basically the commands, telling the GPU what to do fast enough. So these are the walls: memory, compute, and overhead. And basically every optimization you've heard of, like kernel fusion, flash attention, all of this here in the list, Python, CUDA graphs, quantization, all of these are attacking each one of these walls separately. So again, by identifying which wall your GPU program is struggling with, you can just apply the whatever technique you want to directly. So in the GPU performance engineering world, there is this very popular mental model. This is not originally by me, but this is just something people use, which is looking at the GPU as a big factory, where the high bandwidth memory is the loading dock. So here the trucks, they're coming in with the materials to give to the factory floor, which consists of SMs, streaming multiprocessors, and tensor cores. And each of these blocks here are essentially SMs where all the math, all the computation is happening. And then finally, you have the foreman who is basically radioing in what to do to the factory floor. So they get the materials, the foreman, which is the CPU, it's launching kernels and telling the factory floor exactly what to do with the data it has received. So throughout the talk, I'm going to be highlighting each of the sections here in red, depending on what the bottleneck is. So memory, compute, and overhead. So before we start looking at the different bottlenecks, we can first talk a little bit about the GPU we're on. So currently, this notebook here is running on an H100 GPU, and it has specific specs here, which are written here. So the high bandwidth memory, like bandwidth itself, it's at 2 terabytes per second. So that's the amount of throughput we can give to the SMs, essentially. That's like the peak. And then we have the FP16 tensor core peak, which is at the 756 teraflops. So this is like how fast the computation can happen inside the factory floor here, is like in the tensor cores, essentially. And then we have the SMs, which they're like 114 of those in total. So this is again where all the math computation is happening. And then we have an L2 cache. There's no L2 cache here, but you can look at the L2 cache as like a small shelf inside the factory floor where they have very, very fast access. Like the SMs have very, very fast access to the data. So then they don't need to load the data directly here from HBM, but rather they can just read the data directly from the L2 cache. And that's very small, like 50 megabytes only. And then you have the launch overhead. So that's basically the time it takes between the CPU launching a kernel and the tensor cores, the SMs, receiving it. And that's at around 5 to 10 microseconds for the H100. There's also another number which is important here, which is called the ridge point, which I'll come back to towards the end of the talk, which is the peak flops divided by the bandwidth, the peak bandwidth, which is at 378 flops per byte. And that is essentially where the memory ceiling and the compute ceiling meet. I'll come back to this number again towards the end of the talk. We also have a diagram here of the internal memory hierarchy inside the SMs. And we don't need to go too much into detail here, as these numbers is actually all you need, to be honest, in order to do the performance engineering. But you can see that you have each SM consists of tensor cores, which can do the math computation in different quantizations. You also have the cache, which I was referring to earlier. Yeah.